Right now, a telescope somewhere on this planet is pointed at a patch of sky containing thousands of galaxies. Scientists are watching, waiting, listening. And here is what almost nobody talks about honestly. Even if every one of those galaxies hosts 1,000 intelligent civilizations, not one of them is coming here. Not in our lifetimes. Not in the lifetime of our species. Not ever. The barrier is not a lack of curiosity. It is not primitive technology. It is not political will or funding or imagination. The barrier is the structure of the universe itself. This is the argument that cosmologists understand in their bones, but that never quite makes it into the conversations people are actually having. The ones about UFOs, about government disclosure, about whether we have already been visited. Those conversations skip straight to the exciting part. They skip the physics. And the physics is where the real story lives. If you want to understand why the cosmos enforces solitude on every civilization that has ever existed, why intelligence and distance are permanently at war with each other, why the answer to the great silence is written in the equations of relativity and thermodynamics rather than in the footnotes of a congressional hearing, then stay with me. This is going to take a few minutes. It is worth every one of them. Before we go any further, if the last 30 seconds already felt different from every alien video you have watched before, hit the like button right now. Subscribe so the next argument finds you before someone else does. And drop a comment below, one word, one sentence, whatever you want. Do you think we are truly alone in this universe? I read every single one. Now, let us get into it. Part 1. The census problem. Begin with the most generous possible assumption. Suppose intelligent life is genuinely abundant. Suppose the Milky Way contains not dozens, not hundreds, but 10,000 technologically advanced civilizations right now, scattered across its spiral arms like lights in a city seen from altitude. 10,000 civilizations. That sounds like a crowd. It sounds like a neighborhood. It sounds like the precondition for contact. It is not. The Milky Way contains roughly 400 billion stars distributed across a disk approximately 100,000 light-years in diameter. The volume enclosed by that disk is so enormous that even 10,000 civilizations, spread evenly across it, would give each one an average territory of roughly 40 billion cubic light-years. Each civilization would be separated from its nearest neighbor by thousands of light-years of empty space. Think about what that actually means. Not in the abstract. In the specific. A light-year is the distance light travels in 1 year. Light moves at approximately 670 million miles per hour. It crosses the continental United States in roughly a 50th of a second. In 1 year, at that speed, it covers approximately 5.9 trillion miles. 1 light year, 5.9 trillion miles. Now multiply that by 1,000. That is the approximate distance to the nearest hypothetical civilization under optimistic assumptions. 5.9 quadrillion miles. A number so large that writing it out in standard notation stretches across a paragraph. A number that the human brain was never designed to hold. We evolved to estimate distances between trees, between predators and water sources, between villages a day's walk apart. Nothing in our cognitive inheritance prepared us to genuinely feel the difference between a million and a quadrillion. Both numbers register simply as very large, but the gap between them is incomprehensible, and that gap is where the physics of isolation lies. The nearest star system to our own, Alpha Centauri, sits 4.24 light-years away. Every measurement of interstellar distance begins with that baseline. Every discussion of alien contact must pass through it first. At 4.24 light-years, Alpha Centauri is already so far away that Voyager 1, the farthest object humanity has ever launched, traveling continuously since 1977 at roughly 38,000 miles per hour, would need approximately 73,000 years to reach it. 73,000 years. The entirety of human civilization, from the first fired clay pots to the most powerful computers on Earth, spans roughly 12,000 years. Voyager would need more than 6 full repetitions of that entire arc just to reach the front door of the nearest star. And Alpha Centauri is almost certainly not home to anyone. The interesting stars, the ones orbited by planets in the habitable zone with stable conditions and long enough histories for complex life to develop, are mostly not 4 light years away. They are hundreds, thousands. The census problem is not that neighbors are rare. It is that the galaxy is so enormous and neighbors so distant that the word neighbor loses all practical meaning. Even if they exist, the universe keeps them beyond reach. Part 2. The clock that runs against everyone. Distance is a passive obstacle. It sits there. It does not move. It does not change. A sufficiently motivated civilization could look at 1,000 light years of empty space and say, "We accept this. We will build something capable of crossing it." Time is different. Time moves. It operates continuously. It degrades everything it contacts without pause, without exception, without mercy. And for interstellar travel, time is not just a challenge. It is a compounding catastrophe that attacks the mission, the ship, the crew, and the civilization that launched all of them simultaneously on separate fronts. Start with the simplest version. At 10% of the speed of light, an ambitious but theoretically conceivable velocity for an interstellar spacecraft, the journey to Alpha Centauri takes 42 years. One way, not a round trip, just arrival. A crew that departs at 30 arrives at 72, assuming no one dies along the way, assuming the ship functions without catastrophic failure for 4 consecutive decades, assuming the human body tolerates deep space conditions with none of the evolutionary preparation it received for life on a planetary surface with gravity and a magnetic field and a breathable atmosphere. The round trip consumes 84 years, a complete human lifetime. The person who climbed aboard the ship and the person who descends from it share the same biological history, but they share almost nothing else. Their world is unrecognizable. Their connections are dead or elderly. The civilization they knew has rearranged itself around their absence. And this is the optimistic case. This is the nearest star. Scale to a star 100 light years away, a perfectly ordinary distance within the Milky Way, and the same journey at 10% of light speed takes 1,000 years. Not a lifetime, a civilization. 1,000 years ago, the Notre Dame Cathedral had not yet been built. Oxford University had not yet opened. The magnetic compass had not yet reached Europe. A crew departing today would arrive in the year 3025. Their descendants, born aboard the ship, raised inside its corridors, taught the mission's purpose by people who are now long dead, would step onto an alien world at the end of a journey that outlasted every government, language, religion, and cultural tradition their ancestors carried at departure. This is not a romantic adventure. This is an experiment in whether any human institution can survive the conditions the universe imposes on interstellar travel. Every historical example we have says it cannot. The Roman Empire, one of the most durable and sophisticated political structures ever built, lasted roughly 500 years before fragmenting beyond recognition. The Catholic Church has maintained greater continuity than almost any other human institution, across 1,500 years of unbroken operation. The oldest living written language has been in use for perhaps 5,000 years. These are extraordinary achievements. They are also less than half the travel time for a round trip to a star 100 light years away. A generation ship does not merely need to survive a journey. It needs to survive multiple complete cycles of the kind of social transformation that has, on Earth, produced revolutions, religious schisms, technological upheavals, and the complete replacement of every cultural touchstone at least once per millennium. It needs to do this in a closed metal environment with no outside input, no new resources, no fresh perspectives, no possibility of rescue, and no horizon beyond the walls. What happens to a population 500 years into a 1,000-year voyage? The founders are 20 generations dead. Their words survive in records that fewer people read each century. The mission's original justification, whatever it was, has been filtered through 20 rounds of reinterpretation, each one drifting further from the source. The language has evolved. The religion, if there was one, has mutated. The governance structure has been overthrown and rebuilt multiple times. And the destination is still 500 years away. Historians have a word for what happens to isolated groups separated from their origin culture by centuries of distance. It is called divergence. The group does not stay still. It does not preserve itself in amber. It transforms continuously in ways that cannot be predicted or controlled from outside. A generation ship is the most extreme divergence experiment in the history of human social science, conducted without a control group, without the ability to stop, and without any mechanism for the original civilization to verify whether its values, its mission, or even its language survived the crossing. Even if they launched, the universe was already dismantling them from the inside. Part 3. The price tag. Suppose a civilization accepts the time burden. Suppose they design a ship capable of sustaining a population across multiple generations, with robust governance, redundant life support, and self-replicating manufacturing capacity. They are committed. They are serious. They are willing to pay whatever the universe demands. Here is what the universe demands. To accelerate a spacecraft to 10% of the speed of light requires kinetic energy proportional to the mass of the vessel and the square of its velocity. The specific figure for a modestly sized interstellar craft, not a generation ship, just a medium-sized robotic probe weighing roughly 1,000 kilograms, works out to approximately 4.5 times 10 to the 17th joules. That number needs an anchor. The most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, released roughly 2.1 times 10 to the 17th joules of energy in a single explosion. The energy required to push a car-sized probe to 10% of light speed is more than twice the energy released by the largest nuclear detonation in human history. For propulsion alone, without deceleration, without a crew, without life support, without the return trip, a large nuclear power plant generating 1 gigawatt of continuous electricity would need to run for approximately 14 years at full capacity, channeling every single watt of output into acceleration to reach that figure. 14 years of a facility that powers 1 million homes, expended entirely on pushing a single small machine to a velocity at which the nearest star is still a 42-year journey away. This is not a funding problem. This is not an engineering problem. This is physics presenting an invoice, and the invoice is non-negotiable. The energy requirements do not shrink with better technology. They cannot. The kinetic energy of a moving object is determined by its mass, its velocity, and the fundamental constants of the universe. No engine, however efficient, can make the object arrive at its destination with less kinetic energy than physics demands. Technology determines how much of the input energy is wasted on heat and exhaust rather than converted to useful thrust. It can approach the theoretical minimum. It cannot go below it. The minimum is set by the universe, not by the sophistication of the engineer. Now scaled to a vessel capable of transporting even a small crew with the life support, radiation shielding, food production, manufacturing, and structural integrity needed to survive decades in the interstellar void. Such a ship would weigh, at absolute minimum, tens of thousands of kilograms. More realistic estimates for a serious crewed interstellar vessel range from millions to hundreds of millions of kilograms. The energy requirements scale in proportion. A 100 million kilogram ship accelerated to 10% of light speed requires roughly 4.5 times 10 to the 25th joules. The total energy humanity generates in an entire year from every power plant, engine, and solar panel on Earth combined amounts to approximately 5.8 times 10 to the 20th joules. The energy to launch a single serious interstellar mission at a modest fraction of light speed is 100,000 times greater than the annual energy production of our entire civilization. Not 10 times, not 100 times, 100,000 times. No conceivable near-term advancement in human energy technology changes this by more than a few orders of magnitude. And an improvement of a few orders of magnitude still leaves the gap enormous. The universe is not asking for a slightly larger check. It is asking for a check so large that writing it requires inventing a new category of economy. Some argue that sufficiently advanced civilizations, harnessing the full output of their star or their galaxy, would find this affordable. And in a narrow sense, they are right. A civilization commanding the power of an entire star could generate the necessary energy in minutes rather than millennia. But this misses the deeper point. More energy does not make the ship faster relative to physics. It makes the cost of reaching a given speed more achievable for the civilization paying it. The velocity ceiling, set by the speed of light, remains. The energy required to approach that ceiling, set by the equations of special relativity, remains. The civilizational resources consumed by each mission remain proportionally staggering even for a Type 2 or Type 3 civilization. A Dyson sphere civilization could afford the fuel bill more easily. It cannot reduce it. And even if the energy problem were solved completely, the ship would still take centuries to arrive. The radiation would still accumulate. The crew or their descendants would still age. The civilization back home would still change beyond recognition during the wait. The time problem does not bend to energy. They are separate walls, and both must be climbed. Even if they exist, the universe itself keeps them from getting here. Part 4. The void has teeth. There is a version of the interstellar travel problem that scientists discuss only when they are being honest about the full picture. The romantic version involves sleek ships cutting through empty space, silent and purposeful. The real version involves a vessel moving through an environment that is actively, continuously destroying it. The interstellar medium is not truly empty. It contains hydrogen atoms at a density of roughly grams of TNT. That is one particle, 1 microgram, 1 impact. The interstellar medium contains enough particles that a ship with a modest cross-sectional area would absorb thousands of such impacts over the course of a journey measured in decades. Each impact delivers explosive force to whatever material it contacts. The cumulative effect is not a single dramatic event. It is a long, grinding erosion of every surface facing the direction of travel. The solution is shielding, which means mass, which means the energy requirements for acceleration increase, which means the fuel requirements increase, which feeds back into every calculation already discussed, pushing the numbers further beyond the affordable range with every ton of protective material added to the prow. Cosmic rays pose a related but distinct problem. High-energy particles, protons accelerated to near-light speeds by supernovae and other astrophysical processes, penetrate virtually any shielding material with enough residual energy to damage biological tissue at the cellular level and electronic components at the atomic level. They cannot be fully blocked. They can only be partially absorbed. For a crew in transit for decades or centuries, the cumulative biological dose from cosmic radiation almost certainly exceeds survivable limits under any shielding scenario that remains physically practical for a spacecraft. This is not a solvable engineering challenge. It is a consequence of the same high-energy physics that governs the universe at its most fundamental levels. The particles that cause the damage are moving faster than our ships ever will. No material humans have discovered or theoretically conceived blocks them completely. The ship can reduce the dose. It cannot eliminate it. For robotic probes, the radiation problem is different, but not easier. Semiconductors accumulate damage from particle bombardment over time. The crystalline structure of silicon, which gives transistors their electronic properties, is disrupted by the passage of high-energy particles that knock atoms out of their lattice positions. Over years and decades of exposure, this damage accumulates into degraded performance and eventual failure of electronic systems that cannot be repaired from the inside. A probe designed for a 40-year journey must maintain all critical systems through 40 years of continuous bombardment by radiation at levels that far exceed anything encountered in Earth orbit, where the planet's magnetic field provides significant protection. No electronic component humanity has ever built has demonstrated reliable operation under those conditions for that duration. In 40 years, remember, is the journey time to the nearest star at 10% of light speed. Longer journeys to more distant targets extend the radiation exposure proportionally. The void does not merely separate civilizations. It works continuously against any physical object attempting to cross it. Part 5. The Horizon Problem. Every argument about alien visitors eventually arrives at the same rebuttal. It sounds humble. It sounds rational. It sounds like the kind of open intellectual position that thoughtful people hold. The argument goes, you are thinking too small. You are using human-scale technology as your reference point. A civilization a million years more advanced than us would solve these problems through means we cannot yet imagine. We should not project our limitations onto them. This argument is wrong. And the reason it is wrong cuts to something important about what physical laws actually are. The barriers described in this piece are not human limitations. They are not artifacts of our current level of development. They are not problems that a sufficiently long research program will one day dissolve. They are consequences of the structure of reality. The speed of light is not a technological barrier. It is a geometric property of space-time. Every particle, every wave, every information carrier in the universe obeys it without exception. Not because no one has thought hard enough about going faster, because the fabric of space itself encodes the constraint. Matter with mass cannot reach light speed because approaching it requires energy input that approaches infinity. Actual mathematical infinity. Not a large number. Not a very large number. Infinity. You cannot engineer around infinity. You cannot allocate resources to overcome it. You cannot have a breakthrough that reduces it to a manageable figure. It is not an obstacle in the path. It is the shape of the path. The relationship between kinetic energy, mass, and velocity is not a human equation. It is universal. It governs the motion of subatomic particles in accelerators on Earth and the trajectories of protons in galaxies a billion light-years away. It governed matter before the first star formed. It will govern matter long after the last star dies. A civilization commanding the energy of 1,000 stars still cannot reduce the kinetic energy requirement for accelerating a given mass to a given velocity. They can pay the bill more easily. They cannot reduce it. The floor is not set by their level of advancement. It is set by the constants woven into the equations of physics before any civilization existed to read them. And the second law of thermodynamics applies everywhere. Entropy increases in every closed system in the universe without exception. Every structure decays. Every organized system drifts toward disorder over time. There is no technology that reverses this. There is no civilization advanced enough to exempt itself from it. A ship lasting 10,000 years must fight entropy continuously for 10,000 years, replacing components, repairing systems, and maintaining complexity against a universal pressure toward simplicity that never pauses. The advanced civilization argument mistakes the unknown for the possible. It says, because we cannot imagine how they would solve this, we should assume they can. But the barriers described here are not unknown engineering challenges. They are known consequences of well-understood physics. We are not speculating about what might be difficult. We are calculating what is impossible. The distinction matters enormously. Even if they exist, the universe itself keeps them from getting here. Part 6. The signal that arrives too late. Here is something that does not appear often enough in conversations about contact. We have been broadcasting radio signals into space for roughly a century. Those signals, expanding outward at light speed, have now reached stars within approximately 100 light-years of Earth. That bubble of detectability contains perhaps a few 100,000 stellar systems. The Milky Way contains 400 billion stars. Our signal has reached roughly 1 in 800,000 of them. Not 1 in 1,000. Not 1 in 100,000. 1 in 800,000. A civilization orbiting a star 1,000 light-years away has no idea we exist. Not because their technology is insufficient to detect our signals. Because our signals, traveling at the absolute maximum speed allowed by the universe, have not arrived yet. They will not arrive for another 900 years. And when they do arrive, they will have spread across a sphere roughly 6,000 trillion miles in radius, diluted by the inverse square law into a whisper so faint that it sits far below the noise floor of any receiving antenna, whose construction doesn't require engineering feats beyond anything we can currently conceptualize. The universe enforces a delay on every exchange of information between distant points. That delay is absolute. It cannot be reduced. A message sent from a star 1,000 light-years away takes 1,000 years to arrive. A reply takes another 1,000 years to return. A single exchange of information requires 2,000 years, during which the civilization that sent the original message may have changed beyond recognition or ceased to exist entirely. This is not a communication inconvenience. It is a fundamental disconnection between any two civilizations separated by interstellar distances. It means that any civilization aware of our existence is seeing a version of us that is hundreds of years out of date. They are watching us through a window into the past and cannot know whether we still exist, whether we have advanced, whether we have collapsed, or whether the world they see was just a brief, bright moment in a history that has since moved on entirely. And we are watching them through the same window. Every star we see in the night sky, we see as it was when the light we are currently receiving departed. The star 4 light-years away shows us what it looked like 4 years ago. The star 400 light-years away shows us what it looked like 400 years ago. We are surrounded, every night, by an ocean of images from the past, and every civilization we might ever observe would be unreachable not just across space, but across time. The universe does not merely separate us by distance. It separates us by delay. The faster something moves, the more energy it costs. The farther information travels, the more time it takes. These are two expressions of the same underlying constraint, and together they make genuine communication between distant civilizations functionally impossible across any time scale that a civilization can coherently plan for. Conclusion: the architecture of solitude. Stand outside on a clear night and look up. Every point of light you see is a sun. Many of those suns have planets. Some of those planets almost certainly have conditions compatible with life. Some fraction of those worlds may have produced organisms capable of looking up at their own night sky and wondering the same thing you are wondering right now. This is not speculation. It is a consequence of the numbers. The universe is too large and chemistry is too productive for life to be a singular accident. But between every one of those minds and every other, the universe has placed the same set of barriers. Distance measured in years of light-speed travel. Energy requirements set not by the level of technology, but by the invariant constants of physics. Time that erodes ships, crews, civilizations, and purpose with complete impartiality. Radiation that penetrates shielding. Communication delays that make real-time exchange impossible across any meaningful interstellar scale. None of these barriers yield to intelligence. None of them soften with technological advancement. None of them were placed there by accident or negligence. They are the architecture of a universe that apparently produces minds in abundance and then keeps them permanently, irrevocably apart. The silence we hear when we point our telescopes at the sky is not the silence of an empty cosmos. It is more unsettling than that. It is the silence of a cosmos full of voices, each one isolated behind walls of light years and centuries, each one generating signals that arrive diluted to nothing after crossing the void, each one burning for a brief window of time that the universe provides and then quietly, indifferently withdraws. We are not alone in the way that matters for physics. We are alone in the way that matters for everything else. The universe is not hostile to life. It is simply indifferent to the desire of life to find itself in others. It builds the conditions for mind. It separates every mind it builds. And it enforces that separation with the most fundamental laws it possesses. Laws that no amount of intelligence, ambition, or technological sophistication has ever been observed to circumvent. If they are out there, they are looking at their own version of this sky. They are doing their own version of this math. They are reaching the same conclusion. The universe keeps its civilizations to themselves. And the universe does not make exceptions. If this video changed how you see the night sky, then do one thing right now. Share it with one person who still thinks aliens are already here. Not to argue with them, just to hand them the physics and let it do the work. And if you want more of this, the arguments nobody else is making, the numbers nobody else is running, subscribe. Every video on this channel starts from the same place. Not belief, not speculation, reality. The subscribe button is right there. The next video is already waiting.